Hello everyone. In this video, we'll understand about the principle of mathematical induction, and we will also do some proofs using mathematical induction. First of all, let us understand the principle. Let P of n be a property that is defined for integers small n, and let small a be a fixed integer. Suppose the following two statements. One is P of A is true, means whatever may be the statement, you are replacing A instead of N. If that is true, and then number two, if for all integers K greater than or equal to A is also true, means P of K is true. Subsequently, if you can able to prove that P of K plus 1 is true, then the statement, whatever initial statement is, then the statements for all integers N greater than or equal to A, P of n is true. So based on that, we can able to conclude. Now, in the subsequently, we will be seeing some of the formulas or equations or some statements which can be proved using this mathematical induction. In this, we will see how do we prove 1 plus 2 plus 3 up to n equal to n into n plus 1 by 2 using mathematical induction. So first of all, the given statement or the given formula, we will just call that as P of n. So P of n is, P of n B means I will put a colon, 1 plus 2 plus 3 and so on up to n is n into n plus 1 by 2. Now let us consider n equal to 1. If n is equal to 1, then what will happen? It will be P of 1. P of 1 in the left-hand side of the statement, it will be just 1 because n is taking value 1. So that is your LHS. And then RHS, that is right-hand side, will be 1 into 1 plus 1 divided by 2, which is equal to 1 only. Therefore, P of 1 is true. Now, we will proceed with n equal to 2. If n is equal to 2, then left-hand side will have 1 plus 2 because n is equal to 2. So, left-hand side will be 1 plus 2, which is 3. And then right-hand side will be n, that is 2 into 2 plus 1 by 2, that is also 3. Therefore, we can say P of 2 is true. Now, let us assume, let P of K equal to true. P of K be true. Be true. Which means we are assuming n equal to K. So that means our left-hand side will become now 1 plus 2 and so on up to, instead of n, it will become K now. And the RHS will be K into K plus 1 divided by 2. So we are assuming this as true. That means we need to prove now, to prove P of K plus 1 is true. So our left-hand side will be now 1 plus 2 and so on up to K, and then one more term, that is K plus 1. Now, this we already assumed that it is true. That means we can substitute it with, when it is true, we can rewrite this as 1 plus 2 plus 3 up to K is equal to K into K plus 1 by 2. So that can be substituted here, K into K plus 1 divided by 2 plus K plus 1. Now LCM is 2. We can rewrite this as K into K plus 1 plus 2 times K plus 1. So in the numerator, common now is K plus 1. We can take that outside. So inside we will have K plus 2 divided by 2. That can be rewritten as K plus 1 into K plus 1 plus 1, means k plus 2 can be written as k plus 1 plus 1. So we may notice it is very similar to n into n plus 1 by 2. Therefore, p of k plus 1 is true. We have proved, and therefore p of n is true. We can conclude that p of n is true. So that is how we can use mathematical induction in proving some of the statements. In this question, we need to prove that 1 square plus 2 square and so on up to n square is n into n plus 1 into 2n plus 1 divided by 6 by mathematical induction. So let us again consider, let p of n be 1 square plus 2 square plus and so on up to n square, which is the given right hand side, which is n into n plus 1 into 2n plus 1 divided by 6. Now, let us check for p of n. If p of 1, if n equal to 1, then p of 1 will be, first left hand side will have only 1 square, that is your left hand side, which is equal to 1 only. Now right hand side will be 1 into 1 plus 1 into 2 times 1 plus 1 divided by 6, which is nothing but 2 into 3 by 6, and that is also giving you 1. Therefore, we can conclude that p of 1 is true. Now, let us assume n equal to k is true, where k is an integer which is greater than 1. K is an element of a positive integer which is greater than 1. So now we can rewrite p of k as 1 square plus 2 square plus and so on up to k square should be equal to k into k plus 1 into 2k plus 1 divided by 6. Now we need to prove p of k plus 1 is true. So for that, we will write down the left hand side, which will be 1 square plus 2 square plus and so on plus k square plus k plus 1 the whole square. Right hand side will become now k plus 1, and then and then instead of k we have to replace it with k plus 1 wherever k is there. So this will become k plus 1. There is a 1 again, so k plus 1. And then here 2 times k plus 1 plus 1 whole thing divided by 6. This is what we have to prove. This is to prove using from the left hand side. Means now LHS can be written as this term we are already having, which is k into k plus 1 into 2k plus 1 by 6 plus k plus 1 the square. Now the LCM is 6, so we can rewrite it as k plus 1, 2k plus 1 plus 6 times k plus 1 the whole square. Now we may notice the common term in these two is k plus 1 in the numerator. Here in the first term it will become now k into 2k plus 1, because already we took k plus 1 outside, plus 6 times k plus 1, because we took k plus 1 already outside. That will be equal to k plus 1. Let us keep that outside only. Now let us expand this. This will become 2k square plus k plus 6k plus 6. Whole thing divided by 6. Now this is k plus 1. Now this will become now 2k square plus 7k plus 6. Divided by 6. Now the numerator can be factorized. We can write it as 2k square plus 3k plus 4k plus 6 divided by 6. So now this can be again rewritten as first two terms, the common is k. So we can write it as 2k plus 3. Then next two terms, the common is 2. So we can write it as 2k plus 3 divided by 6. Now this can be rewritten as k plus 1. And then here the common is 2k plus 3 times k plus 2 divided by 6, which can be rewritten as k plus 1 and then k plus 2 and then 2k, that 3 can be written as 2 plus 1 divided by 6. That will be k plus 1, k plus 2. Then in the first two terms, 2 is common. We can write it as 2k plus 1 divided by 6. Again, this can be written as k plus 1, then k plus 1 plus 1, then 2k plus 1 divided by 6. So it is very similar to n into n plus 1 into 2n plus 1 divided by 6. So we can conclude that therefore p of k plus 1 is true, and hence we can conclude p of n is true. So that way we can prove this particular statement. In this question, we need to prove that 1 cube plus 2 cube and so on up to n cube is n into n plus 1 by 2, the whole square, using mathematical induction. So let us first consider the given formula as a statement. Let p of n is equal to 1 cube plus 2 cube and so on up to n cube is given as n into n plus 1 divided by 2, the whole square. So now let n equal to 1, then p of 1 will be, here, instead of putting equal to, I will put colon. So in this case, LHS will be 1 cube, which is nothing but 1. Right hand side will be 1 into 1 plus 1 divided by 2, the whole square. That will also be 1. So we can say p of 1 is true. Now let us consider n as 2, then P of 2, in that LHS will be 1 cube plus 2 cube, which is 1 plus 8, that will be 9. RHS will be 1 into, 2 into 2 plus 1 by 2, the whole square, which is, if we look into, this is 3 square is 9. So we can conclude that P of 2 is also true. Now let us assume, instead of saying this, we will assume now P of K is true, which means we will have 1 cube plus 2 cube plus and so on. K cube will be equal to K into K plus 1 divided by 2, the whole square. Now, to prove n equal to K plus 1 is true. So our LHS will become now, since n is K plus 1, we will be writing 1 cube plus 2 cube plus and so on up to K cube plus K plus 1 the whole cube. This term we know, we already assumed it as K into K plus 1, or we can simply write it as K square. This is nothing but K square, K plus 1 the whole square divided by 2 square, which is 4. So I can copy that. K plus 1 the square divided by 4 plus K plus 1 the whole cube. Now the LCM for this is 4. So K square into K plus 1 the square plus 4 times K plus 1 the whole cube. In this, now common is K plus 1 the square. So now here we will have K square, and here we will have 4 times K plus 1 divided by 4. That will be equal to K plus 1 the square, and here it is K square plus 4K plus 4 by 4. And this can be written as K plus 1 the square, and this can be written as K square plus 2 times 2K 2 times 2K plus this is 2 square divided by 4. That will be K plus 1 the square, and this is, if we look into this, this is like A plus B the whole square, which means K plus 2 the whole square. I mean, it is these two are same, because K square plus 2 square plus 2 times 2K, you will get the same thing, divided by 4. And now this can be written as K plus 1 times K plus 2 divided by 2 the whole square. So again, this can be rewritten as K plus 1, K plus 1 times K plus 1 plus 1 whole thing divided by 2 the whole square. So this is nothing but similar to n into n plus 1 by 2 the whole square. So we can conclude that therefore P of K plus 1 is also true. That is what we have to prove. Therefore we can say P of n is true. That is the proof using mathematical induction.